So welcome back, everyone. The second speaker of the day is Jordan Cutler from the Harvard Society of Fellows, and he will tell us about some recent work on black hole microstate statistics and mesoscopic quantum gravity. So please, Jordan, take it away.
Well, thank you so much for giving me the opportunity to speak. So I'm going to tell you about some recent work in collaboration with Christian Jensen. Here's the archive number. It's a paper which appeared earlier this year. So indeed, the title of the talk is Black Hole Microstate Statistics and Mesoscopic Quantum Gravity. In the course of the talk, I'll explain exactly what I mean by black hole microstate statistics, as well as what I mean by mesoscopic quantum gravity. So let's begin with the factorization paradox. Now, wormholes have posed a problem for ADS-CFT since the beginning of when the correspondence was introduced. So let me briefly review the basic puzzle. Let's consider the context of Euclidean ADS-CFT, where we consider quantum gravity in Euclidean ADS and Euclidean conformal field theory, to which it is dual. Now, suppose that on the CFT side, we would like to compute a CFT partition function, here which I've written as Z1. We can imagine that on the CFT side is a partition function where we couple the CFT to a torus, or maybe a sphere across a circle. Now, on the quantum gravity side, on the ADS side, this is computed by computing the partition function for ADS string theory on a background, which is asymptotically ADS, where the asymptotically ADS boundary has the same topology as that of the geometry to which we have coupled the CFT. So that is, the partition function on the CFT side is equal to the partition function on the ADS side, as per the correspondence. Now, suppose we did something that at first seems slightly trivial, where we compute the product of two partition functions on the CFT side. I'll denote them by Z1 and Z2, even though they can be identical to one another. Now, on the ADS side, what this corresponds to is computing the partition function with two asymptotically Euclidean ADS boundaries. Now, when we perform this computation, say in a semi-classical expansion, if we have small g Newton, then what happens if, when we impose these boundary conditions, we additionally find that there are connected contributions to the partition function? Well, this seems to be a problem. And the reason it's a problem is because on the CFT side, we just have two independent CFTs, and the product of their partition functions trivially factorizes. But on the gravity side, if there are indeed these wormhole contributions, then we naively do not have factorization on the gravity side. So this emphasizes that we should ask the question, do there exist wormhole contributions on the gravity side of the correspondence, which would contribute to a product of two partition functions on the CFT side? Now, again, this is related to asking, for instance, if there are wormhole solutions with two asymptotically ADS boundaries. Now, there have been, if in fact there were such contributions, which we'll comment on further in a moment, then it has been proposed that maybe we should interpret the CFT side differently. Maybe we should think about the CFT side as some form of ensemble average. Maybe we're averaging over couplings over different CFTs. It depends exactly on what one believes, but the basic point is that if there are wormhole contributions on the gravity side, then something fundamental has to change about the standard ADS-CFT dictionary if we are to have non-factorization on the CFT side, if we want the two sides to match. So let's focus on the question of whether there are these wormhole contributions in ADS gravity. So in the context of vacuum, the vacuum Einstein's equations, it was shown, due to a famous result of Witten and Yau in '99, that there are no vacuum ADS wormhole solutions to Einstein's equations, in particular for boundaries with non-negative curvature. Of course, in full-fledged ADS-CFT, we always have matter fields, we also have strings and branes that can live on top of the spacetime, which might act to stabilize potential wormholes. So in fact, there are a few examples of these kinds of wormhole solutions in full-fledged ADS-CFT. However, they're not known to be stable, either perturbatively in fluctuations of the matter fields or even metric fluctuations, or to brains or other kinds of extended objects. Here is a sampling of some papers which discuss these kinds of wormholes. So I would say that the status of ordinary saddles, which form wormholes, which have two asymptotically Euclidean ADS boundaries, is presently unclear. For a good review of the state of affairs, I recommend the introductory section of this paper last year by Marolf and Santos, or the introductory section of my recent paper with Christian Jensen. However, there have been some new examples in the last few years of these would-be wormhole solutions, which are inspired by developments in low-dimensional gravity. By low-dimensional gravity, I specifically mean Jakob-Teitelbaum gravity, or nearly ADS2 Jakob-Teitelbaum gravity, which is in 1 + 1 dimensions. This is due to the work of Schaefer and Stanford. In fact, many features of this work can actually be generalized to higher dimensions, and in the context more of full-fledged ADS-CFT, which was implemented in a series of papers by Christian Jensen and myself, although we'll get into more details of that and related matters later. Now, the wormholes that under consideration here are interesting because they encode physics about black holes. Now, the wormholes which I mentioned on the previous slide it's not quite clear what their interpretation should be or whether they encode any interesting physics. They're just constructions of wormholes for the sake of being wormholes. But what's interesting about the wormholes that are inspired by these low-dimensional gravity examples is they tell us interesting physics. So as such, they have a reason to be. They have a reason to be there. We don't necessarily want to get rid of them because they tell us interesting information. So now the factorization paradox, which over the history of ADS-CFT has been previously largely ignored, has new urgency due to the presence of these wormholes, which I will tell you more about. So that is, there really do appear to be wormhole contributions on the ADS side of the partition function computation, which really brings into question what is going on the CFT side of the computation. Is there factorization? Is there non-factorization? What gives? What's going on? So let me say rather dramatically that our understanding of ADS-CFT is here at stake. That is, we may potentially have to radically change the ADS-CFT dictionary, contingent on what is the role of these wormholes and how they map across the duality. Let me say more about the new examples that I alluded to. They come in two different kinds. One is in the form of complex saddles. This is the so-called double cone geometry, which in fact can be regarded as a complex saddle solution to the Einstein field equations in vacuum, and you can consider what happens when you couple it to matter. Now, the proposal of Schaefer and Stanford in the context of low-dimensional gravity is that this, on the CFT side, is equivalent to some kind of ensemble average over the product of two partition functions, of trace of e to the minus ith, where h is the Hamiltonian of the CFT, trace of e to the ith. T is a scalar, h is the Hamiltonian operator. Now, in the context which they consider, namely the SYK model as well as Jakob-Teitelbaum gravity, the theories in question are in fact dual to ensemble averages. So the idea of, or literally ensemble averages in the case of SYK, manifestly. So in that setting, it makes sense to talk about the ensemble average in a CFT type description. The point, however, is that these kinds of double cone geometries actually seem to exist in higher dimensions outside of the purview of these low dimensional examples, which are dual to ensemble averages. So that is, these double cones, these complex saddles, appear to exist in higher dimensions, even where an ensemble average interpretation apparently is not present. However, the status of these complex saddles is unclear, especially when you couple to matter or couple to strings. One can regulate the cone point in various ways, but I would say that a full stability analysis and rather a full understanding of what it means to have a complex saddle and coupling to matter in various ways is as of yet unclear and not resolved. On the other hand, we have Euclidean constrained saddles due to the work of Christian Jensen and myself over the last few years. Now, this is a fully Euclidean kind of approach to the problem. It's not a complex saddle, but it's Euclidean saddle. But the issue, in fact, is that it's not a saddle in the ordinary sense, but it's rather a constrained saddle. So what do I mean by that? Well, what I mean is that let's consider these wormhole metrics, which can be described explicitly, where say the boundaries are a sphere across a circle, where the circle on the left side has circumference beta 1, and the sphere across the circle factor on the right side has circumference beta 2, and the wormhole has a bottleneck volume which goes like b to the dimension, or rather the circumference of the bottleneck you can regard as being b. Now for fixed bottleneck, if you fix the bottleneck, which in fact can be done in a different variant way, it turns out, then you do have a saddle. But of course, what a genuine saddle is, rather a saddle of the full Einstein's equations, is one in which we allow all of the fields, all of the fluctuations to vary. So if we allow the bottleneck to vary, we find that this is not actually a genuine saddle. You can think about it as a valley, as a sloped valley of saddles or near saddles. Namely, these are a one parameter family of configurations which are stationary in all directions in which you can fluctuate, except for the direction that changes the size of the bottleneck. So it turns out that the contribution of these kinds of wormhole solutions to the partition function is in fact given by the integral over these configurations, where you integrate over the bottleneck. So you integrate over the bottleneck length going from 0 to infinity. And in fact, what this gives you in situations in which we understand that there should be an ensemble dual is this gives you trace of e to the minus beta 1h, trace of e to the minus beta 2h with some kind of ensemble average. I should really emphasize that when I write these squiggly equalities, I should really have written the connected contribution of this and this. These are the connected pieces. There are also the disconnected pieces, which in fact dominate. Now, these kinds of Euclidean constrained saddles can be embedded into string theory. And the full amplitude, but one drawback is that the full amplitude is not computable in effective field theory in d greater than 3 space-time dimensions. So here's the basic issue. For d less than 3 space-time dimensions, or less than or equal to 3 space-time dimensions, that is in 2 Euclidean dimensions or 3 Euclidean dimensions, there are no propagating gravitons in the bulk. There's only boundary gravitons. As such, there's not an energetic cost to shrinking the bottleneck to 0 size. However, in 4 and greater Euclidean space-time dimensions, there's a Casimir energy, which effectively blows up as we make the bottleneck very, very small. So this computation breaks down in effective field theory in 4 and greater space-time dimensions as we take the bottleneck to 0 size. So there are various things that one can do to get around this. But I would say that in both cases, the state of affairs is not satisfactory. On the one hand, we have to contend with complex metrics and the cone point and regulating the cone point and coupling to matter fields in the case of this double cone. And in the other case, in the case of Euclidean constrained saddles, we have to contend with the fact that in 4 and greater space-time dimensions, which is the case that we're interested in for the ordinary examples of ADS-CFT, we have to contend with the fact that as the bottleneck shrinks to 0 size, we have to deal with the fact that the effective field theory approximation breaks down, which in fact is a potentially serious problem. The goal of this talk is going to be to solve both of these problems by a new approach, by a new construction of wormholes that will still reveal similar physics about black holes, which I'll tell you about shortly. So the rest of the talk is going to be divided into 4 parts. The first part is a discussion of black hole microstate statistics, in which I will tell you about the physics which is encoded by these wormholes. In the second part of the talk, I'll explain some new entries in the holographic dictionary, namely new kinds of wormholes and what they correspond to on the CFT side. In part 3, I'll show you how we can leverage the technology in part 2 to perform precision tests of black hole microstate statistics across the ADS-CFT duality. And finally, in part 4, I'll explain what I think is the broader perspective which is suggested by these computations, a perspective which I will encapsulate by the name mesoscopic quantum gravity. So let's begin with part 1, where I'll discuss black hole microstate statistics and what is the meaning of these wormholes and what is the physics which they encode. So let me start with the cartoon of a black hole. Now, famously, a black hole radiates approximately thermally with the temperature inverse in its mass due to quantum effects, and has a finite entropy proportional to its area and inverse to g Newton. Now, if we try to compute the quantum state of the black hole, like the reduced density matrix, say, of the black hole, we should regard this as an approximately thermal state, approximately a Gibbs state, where I'm going to refer to these EIs, these states, as black hole microstates with energy EI. Now, a difficult non-perturbative question in quantum gravity is as follows. What are the black hole microstates and what are their energies? The reason that this is a challenging non-perturbative question is that the difference between adjacent energies, the level spacing, is non-perturbative in g Newton. It goes like e to the minus 1 over g Newton. So being able to access the states and even just the individual energies is a non-perturbative question in quantum gravity, and a difficult one at that. What we're going to be focused on in this talk is ways of accessing not the energy eigenstates, but rather the energies themselves, and understanding the statistics of the energies, these EIs. So here I've drawn a cartoon of the level spacings of a putative black hole, or rather the actual individual levels of the black hole. So we can imagine this is continuing on to the right, but I've cut off the graph. So we see that the states increases in density at higher energies. Now, due to very famous results by Hawking, as well as those of Gibbons and Perry a few years later, it's well known that we can access the coarse-grained density of states. So let's coarse-grain the density of states. Here's the coarse-grained density of states where I've smeared over these individual levels so that we just see what the density is. That this coarse-grained density of states, or in fact its Laplace transform, can be accessed by a computation in Euclidean gravity, namely a saddle point approximation in the Euclidean gravitational path integral. This, in fact, is one of the slickest derivations of the Hawking temperature, the one that's well known to practitioners in quantum gravity. So here that we see that there is a one-sided saddle in Euclidean gravity, which accesses the coarse-grained density of states. But suppose that we want to access more refined information. Let's go back to our picture of the individual levels of the black hole. And let's suppose that we zoom in on a part of the spectrum. So here we've zoomed in. We've zoomed in onto a region in which the average level spacing is roughly the same across this region. That is, there's an average level spacing that I'll call delta, which goes like e to the minus 1 over g Newton, non-perturbatively small in g Newton. Now, since black holes, there's much evidence that black holes are chaotic quantum systems. We expect on general grounds that chaotic quantum many-body systems have energy eigenvalues that experience level repulsion. That is, we expect that the nearest neighbor levels, and in fact, even levels which are an order 1 number of level spacings apart, for example, should have a proclivity to repel one another in a universal fashion, which is can be computed by, or rather can be predicted by random matrix theory calculations. So the next most refined thing that we could access beyond just the density of states would in fact be level statistics, 2-point functions of the energies. In fact, what is suggested, or rather what is borne out by these works that I alluded to before, is that in fact, there are wormhole contributions which allow us to access the connected part of the level statistics of the black hole microstate spectrum. As such, this can be regarded as a generalization of the work of Hawking, Gibbons, and Perry. This is a generalization that allows us to access the level statistics of black hole microstates, of course, coarse-grained. Now, the pattern ostensibly continues, even though it hasn't been borne out in higher dimensions. If we look at wormholes that have 3 boundaries, that should allow us to access the connected level statistics, and so on and so forth to higher numbers of boundaries. Although we're going to be concerned with the 2-boundary case for the talk. But anyway, this is the sense in which these wormholes encode information about black holes. These kinds of wormholes that we're going to be interested in tell us about the level statistics of the black hole microstate spectrum.
Excuse me.
Yes.
So what's the meaning of this averaging over E and E prime?
Yes. So let me explain what it is in this case first, in the case of the density of states. So you can think about the true density of states as being a sum of delta functions. In fact, you can see that this is just a sum of deltas over here. Now, a way to think about the coarse-grained density of states is to smear out the delta functions, for example, to replace them by Gaussians or something like that. That will give you this sort of smoother density of states. Now, what the uncoarse-grained level statistics looks like is a delta comb. It would look, perhaps I should have written out the equation, let me say it in words. It'll be a sum over I and j of delta of EI minus E times delta of EJ minus E prime. That is, it's a two-dimensional delta comb, which expresses the level statistics. And we're replacing these, each of these, and what we're doing is we're smearing out this distribution. We're taking this two-dimensional delta distribution and we're smearing that out. And that is the object which we are accessing. So that's why it's only a function of two energies. Does that make sense?
But maybe you do have an exact definition of row 2, right? It's just product of row 1, row 2 rows, or
so that would be the connected piece. But well, so let's put it this way. Oh yes, row 2. Yeah, sorry. Row 2 without the angle brackets is indeed just is just the product of it's just row E prime. It's the product of these two delta combs. The point is that you take that object and you smear that object. And now you just get a function of E and E prime.
But okay, so how this connected piece arise? By just multiplying. That is actually your original question, right?
So what it means is, let me say it this way. What it means is that so here's what I mean. You take the actual row without the angle brackets and you look at row E prime. Then you coarse grain that and you subtract out the product of angle bracket row E, angle bracket row E prime. So you subtract off the disconnected product.
No, I was just asking, not the subtraction. You can forget about just how I mean just multiplying two rows can produce this connected piece.
Oh, it's because,
or maybe you are talking about the connected piece by certain again, I mean some average, and what that average is.
Yeah, so let me see how to explain. I mean, the point is, this object essentially is capturing the density that you have. Well, let me think about how to say this.
Okay, so let me ask you again. I mean, so we want to understand the appearance of this wormhole and whether it is coming from this averaging or it comes before. I mean that it's by taking some average inside the integrand.
Yes. Got it. I think I understand what you're asking. You're asking literally what prescribes what the average is.
Exactly.
Yes, good. So, okay, great. I will address this question shortly with a very explicit formula. Sorry, now I understand your question. Thank you. The answer is that, in general, there are many ways of doing the averaging, which will get you this answer up to small corrections, which will get you the universal prediction of random matrix theory up to small corrections. There's many different ways of doing the averaging. The question which maybe you're asking is, what is the averaging which is picked out by ADS-CFT? Is that right? Yeah. Let me defer that to 2 slides. I'll write down a formula and ask me again. I'll point it out. But at the moment, I haven't said that yet, but I'll write down an explicit formula for what I mean by this. Is that okay?
Yes.
Great. Okay, so now let me tell you some new entries in the holographic dictionary, which will address your question. So let me mention a perspective, a philosophical perspective for the moment. So there's a way of curing the pathologies of the two-sided wormholes which encode black hole microstate statistics. To do so, we have to modify our conception of how to resolve the factorization paradox. And this will be made clear in equations, but let me say it in words first. The idea is that two-sided wormholes in ADS string theory, we're going to find two-sided wormholes in ADS string theory, which correspond to a boundary quantity, namely a CFT quantity, in which the two CFTs are coupled by a joint constraint. I'll write this down in an equation to make sense of it. That is, we are going to see that the bulk wormholes, which don't factorize, are dual to a boundary quantity for two CFTs, where the two CFTs are mutually constrained in a certain way, so that that quantity does not factorize. That is, a non-factorizing quantity in the bulk will be dual to a non-factorizing quantity on the boundary. As such, there is no factorization paradox. Neither of the quantities is supposed to factorize. So let me now tell you, which I think will be the answer to the question, what the story is. Suppose we have the exact partition function of a CFT, namely like this delta comb. And let me have two replicas of it. Row of CFT, the two CFTs can be identical. Row of CFT1 of E1, row of CFT2 of E2. And it'll be convenient later to do some Laplace transform, but this part is not so important, at least conceptually. Here's the manner in which we are going to do the smearing or the averaging. What we're going to do is we're going to force that the energy of E1 plus the energy of E2 equals some total energy. And then we're going to average, this is a joint constraint, and then we're going to average over E1 and E2. This is the nature of the smearing. This is the smearing that we're going to do. It's the smearing that we're going, and in fact, we can consider a delta function, which is a little bit spread out. It can be like a Gaussian, in fact. That's more literally what we're going to do. We'll consider a slightly smeared version of the delta function. But this is the kind of smearing that we're going to consider. And note that this is a smearing which couples together the two CFTs, their partition function. It's a non-factorizing quantity. And what it is dual to on the ADS side is a wormhole with a fixed bottleneck, where the size of the bottleneck is a function of this total energy. So this is going to be one of the main results, that a particular wormhole contribution on the ADS side with fixed bottleneck is going to be related to this CFT quantity, where we have a two replica quantity where there is a joint constraint, which in fact, when we integrate over E1 and E2, implements the kind of smearing that we're interested in. Does this at least partially address the question from before of what
I
smearing?
think so, yes. So what you are saying is that this so-called joint constraint delta function is giving bridge, while this averaging process is just smoothing out. So maybe that's what you are suggesting, right?
That's right, exactly.
Okay, thank you very much.
Absolutely. And this perspective and this equation and result is part of this new work with Christian from this year. So now I will explain it further. So how do you compute this? Well, let me talk about how you compute the right-hand side. There's a slightly more elaborate story as to how to establish that it equals the left-hand side, but I'll give you the flavor for the argument. So what we do is something seemingly unusual. So let's start in the following way. Let's consider a two-sided Euclidean ADS d plus 1 wormholes with boundary topology S1 cross ST minus 1. So here's a cartoon, the wormhole with S to the d minus 1 cross section. Let's fix the renormalized asymptotic lengths of the two circle factors to be beta 1 and beta 2 respectively. So here they are. Now what we're going to do is we're going to additionally fix E1 plus E2 to be equal to E total. So how do we implement this? Well, what is E1? Well, E1 is 1 over beta times the integral over the holographic, the tau component, that's the circle direction, of the holographic stress tensor on the left boundary. And E2 is 1 over beta 2 times an integral over the right boundary times the holographic stress tensor there. This is what we mean by E1 and E2. And to find a single wormhole saddle, when we fix these boundary conditions, we find a single wormhole saddle with bottleneck volume that goes like E total, namely the sum of E1 plus E2. So we're going to fix this sum by putting a delta function in the path integral. So this is a new kind of non-perturbative effect in quantum gravity, and let me explain why this is so strange. So usually, when we compute saddle point approximations, what we do is that we fix asymptotically, in this case, Euclidean ADS boundary conditions, and then we can fix, for example, moduli of the boundaries. For example, we can fix these asymptotic lengths, and when we do so, that usually pins down a particular saddle. So when we do so, either we find a saddle or we don't find anything. We find that there are no solutions to the Einstein field equations, maybe with matter, with those boundary conditions, asymptotically ADS with fixed moduli. However, what's surprising about this is that we are imposing an additional constraint on top of the usual boundary conditions that we would do for Euclidean ADS. So what's actually going on is that we would expect that this problem is over-constrained as a boundary value problem. But nonetheless, this pins us to a particular metric configuration that has a good semi-classical expansion in the gravitational path integral. So let me say that in a slightly different way. These configurations that we are finding here are not saddle points of the Einstein field equations. They are saddle points of the Einstein field equations only after you impose this fixed energy constraint. So in other words, these are not classical solutions, but they are semi-classical configurations in the path integral once you do this, this fixed energy constraint. So that's why this is a new kind of non-perturbative effect in quantum gravity. It is a saddle that you get after you fix some constraint, which you can do in a gauge invariant way because these energies are boundary quantities. So you can do, so this constraint is one that is a diff invariant constraint. And when you impose the constraint by putting a delta function in the path integral, you then get a good saddle point approximation with that constraint imposed. You can think about this, if you will, as some kind of microcanonical constraint. It's some kind of microcanonical constraint that ties together two boundaries. So let me now just explain that you can do this for the full-fledged examples of ADS-CFT. For example, you can consider wormholes in type 2B string theory on ADS5 cross S5, which is the original example of ADS-CFT due to Maldassine in 97. So in particular, you can consider the type 2B supergravity path integral with two asymptotically ADS boundaries. And it has a saddle of the form previously explained, namely where you do this joint energy constraint. So here is what the metrics look like, and the dilaton is constant. Here's the phi-form flux. And in fact, what you find when you run through this, when you run through this computation that I outlined before, is that this describes random matrix theory energy level repulsion of the black hole microstates. It gives the answer that you would expect from random matrix theory. Moreover, I won't get into these details here, but the answer is robust to certain stringy effects that we can compute, such as D3 anti-D3 brain nucleation, although I won't talk about that here. Let me now tell you some precision tests of black hole microstate statistics along the lines of what I told you. I'll tell you some surprising ways in which we can really push this technology that I explained, push these calculations to a remarkable conclusion where we can see a very striking match between a bulk computation and a boundary computation, which we should really regard as a universal random matrix theory computation, which I'll explain shortly. So let me show you a computation which at first might seem rather unusual. Let's suppose that we are in the setting of ADS5 cross S5 type 2B string theory. And we consider the two boundary CFTs at a fixed value of the Yang-Mills coupling. Now we're going to do something weird. We're going to take one of the CFTs and we're going to detune the coupling. Namely, we're going to take the coupling and we're going to add a small perturbation to it. That is, we are asking if we can find the level-level statistics between two different CFTs that have different but similar couplings. Namely, one has G Yang-Mills and the other has G Yang-Mills plus a small perturbation. What this corresponds to when we run through the technology of the computation that I explained before is that this corresponds to a wormhole type configuration in which the dilaton, which is dual to the Yang-Mills coupling, interpolates between two values on the different boundaries. So we find a wormhole, a putative wormhole, which is dual, which appears to be describing level statistics between two CFTs with slightly different couplings or between two copies of n equals 4 super Yang-Mills specifically, with slightly different couplings. So here's the kind of quantity which we're computing by these angle bracket with a C. The C stands for constraint. This corresponds to this, this constrained smearing that I explained before, where we force E1 plus E2 to have to add up to a common energy E total. Now, to write the answer in a slightly nicer way, I'm going to take beta 1 and write it as beta plus IT. I'm going to analytically continue the answer in beta. We'll take beta 1 to beta plus IT and beta 2 to beta minus IT. So I'll write it in this way. The answer that we get has this form. Now, for delta G Yang-Mills equals 0, this term will go away. What we'll find up to a multiplicative constant is a linear dependence in T. That is the answer that you would expect from random matrix theory. That is a universal signature of level repulsion. However, when we turn on G Yang-Mills, when we look at slightly different couplings, or sorry, when we turn on delta G Yang-Mills, namely we make the couplings a little bit different, we see that we get an exponential decay. This is a positive number. So we get an exponential decay in T. That is to say, when you look at level statistics between two CFTs with slightly different couplings, that their eigenvalues are mutually exponentially decorrelated, where the strength of the decorrelation is related to the size of delta G Yang-Mills, how different the couplings are from one another. So a question is, okay, we find this answer. This is done by a gravity computation, a quantum gravity computation. Well, what can we match it to? Is there any CFT computation which would potentially agree with this answer? Because again, this is obtained purely by a gravity computation. So amazingly, there is a computation, a universal computation in random matrix theory, in a particular area of random matrix theory, which is lesser known, called parametric random matrix theory, developed by Altshuler and Simons in 1993. They show that by a single replica computation, namely something that only involves features of a single CFT or a single bulk dual, or rather a bulk dual with a single asymptotically ADS boundary, that you can compute a prediction for what this should be using these random matrix theory techniques. And what's amazing is that we find a precise match, namely that this computation which we get from gravity, which putatively we would like to believe describes the correlations between CFTs with slightly different couplings, and n equals 4 super Yang-Mills, actually precisely agrees quantitatively down to this precise form of the exponential with this random matrix theory computation, this universal random matrix theory computation. So that's extremely surprising. This is a precision test in the sense that we can precisely map the functional dependence of the exponential down to the factors of pi, 32, etc. So let me tell you about one other kind of example, another type of setting. So suppose that we look at wormholes in which we insert a single D3 brane with 1 unit of RR flux.
Excuse me.
Yes, a question.
I just lost the why the coupling change.
Oh, why is the coupling? You mean what in the bulk
Oh, you mean, oh, I'm sorry. So it's just a setup. Okay.
That's the setup, yeah. So it turns out that the wormhole, which is dual, which gives you this information, is one in which the dilaton interpolates between two different values on the two different boundaries. Because that makes sense, because the value of the dilaton is, the dilaton is dual to the coupling. So the boundary value of the dilaton on the two boundaries is actually different, and the dilaton interpolates between them in the bulk. So let's do another kind of example. So let's insert, as I said, a single D3 brane with 1 unit of RR flux. Now, a tentative interpretation is that this would correspond to correlations between SUN super Yang mills and SUN+1 super Yang mills. So what we have in mind is a D3 brane which is extended along the S1 cross S3, but is at a particular point on the S5. So here is the tentative, this is what we expect on the CFT side, that we're looking at the statistics between the Hamiltonian of n equals 4 super Yang mills for SUN super Yang mills, and here this is SUN+1 super Yang mills. Now, this is the answer that we get on the gravity side, and indeed, this this has an exponential dependence on n and t. It actually contains a phase factor. And at present, we actually don't have a way of checking this with the random matrix theory computation. The random matrix theory prediction is not presently known, but appears to be computable using Afitov's SUSY sigma model method. This is some piece of work in progress. But anyway, it seems that the technology that I explained of these kinds of these gravitational path integrals with constraints allow us to access correlations between CFTs of different kinds, whether it's by changing the couplings or even doing something as dramatic as changing the n of the SUN. Now let me explain what I think the broader perspective is, which I'll call mesoscopic quantum gravity.
Sorry, Jordan.
Yes.
May I ask one quick question about your previous slide?
Absolutely.
So this computation you did at fixed n, right?
Well, the point is that from the bulk point of view, because the D3 brane soaks up a unit of flux, there's essentially a different amount of flux on each side of it. So one of the asymptotic boundaries really has n+1 units and the other has n.
Okay. But so if you take like a large n limit, let's say, how do I interpret your result?
How do you interpret the result? What's
in the sense that does this unit of RR flux becomes irrelevant if you take like some large n limit, or?
Well, so no, in the sense that well, how do I say it? So let me maybe say it like this. Suppose we put k units of RR flux, so it's n plus k. A k will appear here.
Right.
The point is that it appears in how do I say? There's still a 1 over n expansion going on, but you can still, a k will still appear. So you can see something about the number of units of flux that you're adding. There's nothing contradictory about that, but I just mean that if you replace this with k, the k will appear here. I mean,
okay.
Let's put it this way. The order of limits is the following. You fix the value of k, and then you take n to infinity.
Okay.
Does that make sense?
I see. Thank you.
Sure. Yeah, I mean, these computations really only make sense, of course, for small g Newton or for large n. So anyway, okay. So let me give this perspective of mesoscopic quantum gravity. So in condensed matter physics and in other subjects, they talk about mesoscopic physics, meaning physics which is not really microscopic, namely isn't really the full UV story. And of course, often what people mean by UV in condensed matter physics is thinking about electrons and lattices and so on. So it's not a microscopic description, but it's not also, but it's also not a completely long wavelength description. It's something in the middle. And what I'm going to propose is that the developments which I've explained to you today, as well as other related developments which have been going on recently in ADS-CFT, for example, Tom Hartman's talk, and various other talks that have happened previously, that they are encapsulated by a framework that I'll call mesoscopic quantum gravity, which I'll try to articulate what it is. So we found, at least in this talk, that a large class of wormholes in ADS-CFT are due to a joint smearing over the energy levels of two CFTs. Moreover, these are CFTs for which one can perform a stability analysis reasonably explicitly, and for which they do not have the pathologies of either the double cone or the constrained instantons, the constrained saddles. So these objects are really actually very nice objects from the point of view of the gravitational path integral, and they are objects for which there is no factorization paradox, because neither the bulk quantity nor the boundary quantity factorizes. But anyway, the point was that what was important for this is a joint smearing over the energy levels. The smearing, or this delta function constraint, which instantiates the smearing, was important. It was essential, in fact, to get the answer right. Also importantly was that something that I slipped under the rug that I didn't say, is that these wormholes only contribute for energies above the black hole threshold. So it's recently been emphasized that the gravitational path integral can only access simple functions of G Newton. This is an argument in a recent paper due to Schlenker and Witten. Now, this actually implies, so the reason why this is the case is that when we perform a semi-classical path integral, for example, where G Newton is a small coupling, well, we can perform, we essentially have saddle contributions, which go like e to the -1 over G Newton, and then we have, we have loop effects, which are polynomial in G. But these are pretty simple functions of G. We can't access most kinds of functions of G in a gravitational path integral. What that means on the ADS side is that if there's any interesting information in ADS-CFT, which is a kind of a non-trivial function of n, we can't access it in a semi-classical expansion, in a large n expansion, or dual to that in the appropriate regime, a small g expansion. Now, for our purposes, this implies that the gravitational path integral can only access smeared energies in smeared energy eigenstates. That is, we can't really fix the energy. That when we're computing the gravitational path integral, it's always up to corrections that are related to the fact that we're computing a small g expansion. So really, the only thing that we can access when we fix the energy, even when we fix this delta function constraint, is that the gravitational path integral has some resolution to it. It essentially smears out the delta function in some particular way. So the only thing that the gravitational path integral can really access, I really want to emphasize this, is smeared energies and smeared energy eigenstates. Now, above the black hole threshold, physics is non-integrable. We can really only access the physics of individual black hole microstates by either smearing in the energy domain and using a semi-classical description, or exact diagonalization of the Hamiltonian of the dual CFT. Now, what we've discussed is smearing in the energy domain, namely not accessing an individual black hole microstate, but a band of black hole microstates. So smearing over energies to access a semi-classical description of a chaotic quantum system is actually an old idea, although perhaps it's a new idea to quantum gravity. So let me draw this cartoon of a particle in a stadium bouncing around. This idea of smearing over energies to access semi-classical descriptions of chaotic quantum system was originally developed by Berry, Bogomolny, and Heller and others in the 70s and 80s under the purview of classical, or rather of quantum chaos. Now, Berry really emphasized in his work that without energy smearing, a semi-classical description of a quantum chaotic system is impossible. In particular, he emphasized that if you want to describe an individual eigenstate of a chaotic quantum system, then there is no semi-classical way of describing it unless you do some form of smearing. That is very much related to the situation that we appear to be in quantum gravity, that if we want to have a semi-classical description with a smooth spacetime, then we have to do some kind of smearing in energy or otherwise. So let me share some intuition about what we can and probably cannot learn from ADS-CFT. For black hole physics, which is chaotic, we can only leverage semi-classical methods to access energy-smeared quantities in practice, at least at the moment. That's the best that we can do. This is the regime for which a smooth semi-classical spacetime makes sense. Moreover, we can only learn about the microstructure of black holes and spacetime in a statistical manner, namely by looking at statistics ingrained in the energy average quantities. This is the perspective that I have been leveraging in this talk and in this work with Christian Jensen. Well, it's in principle possible to access black hole microstates directly by diagonalizing the CFT Hamiltonian, say on a quantum computer, or if you have a powerful enough classical computer to diagonalize the Hamiltonian of n = 4 super Young mills. It's in principle possible. But on the one hand, that is a highly complex operation, computational, potentially intractable unless you have a quantum computer. And even if you have such a state, a black hole microstate in hand, a particular eigenstate of n = 4 super Young mills above the black hole threshold energy, you still have to contend with the fact that the holographic dictionary which describes the black hole interior may still be exponentially complex. So it might be a futile exercise that even if you had access to such an energy eigenstate of the CFT, that really extracting the black hole physics is probably still intractable. So I think the state of affairs can be summarized by an analogy. So let's go back to this famous paper by Einstein in 1905, where he looked at the statistics of pollen in water. He looked at the Brownian motion of pollen in water, and by looking at the fluctuations, the Gaussian fluctuations of the pollen grains, he used this to infer the existence and size of the constituent atoms of the water molecules that were bombarding the pollen grains. Now, this can be done even though the relative size of the pollen of the fluctuations that are being observed and the atoms are related by something like 6 or 7 orders of magnitude. That even though the water molecules are essentially 1,000,000 times smaller than the pollen grains, by still looking at fluctuations that you can observe almost with the naked eye, statistical fluctuations, you can infer something about the microscopic constituents of the water in which the pollen grains are suspended. So this again was Einstein's great insight, and this was verified by kind of experimentally, I guess, by Pohang in 1908. I think the state of affairs in quantum gravity is analogous. I think that what is emerging is a subject of mesoscopic quantum gravity, in which by looking at not the UV physics, but statistical mesoscopic physics of quantum gravity, we can use these statistical properties to infer properties of the microscopic structure of space-time. That is, non-perturbative effects in quantum gravity, which are valid in effective field theory, contain statistical signals of UV phenomena. I think this has the potential to open new horizons in quantum gravity, that pushing in this direction, I think, will be extremely fruitful. And I think this is also a good way of encapsulating many of the developments in recent years in Euclidean wormholes and replica wormholes and so on and so forth. I think, though, that it's important that we, as a field, that we push these developments in the direction of understanding higher dimensional gravity, namely gravity above 3 space-time dimensions, in which that we look at the standard candle examples of ADS-CFT and try to push some of the techniques of lower dimensional gravity into the purview of higher dimensional physics, which I think lead to more realistic models of our world. Let me end, before taking more questions, with a story. Here's just a picture of some old map. But I'm going to tell you just a quick clip from a story by the Argentinian writer Jorge Luis Borges called On Exactitude in Science. The story is only about a half a page long, but let me read you an excerpt and I'll summarize it. He says, the cartographers' guilds struck a map of the empire, whose size was of the empire, and which coincided point for point with it. In the deserts of the West, still today, there are tattered ruins of that map, inhabited by animals and beggars. In all the land, there is no other relic of the disciplines of geography. So what the story is about is it is about a kingdom in which the king has a competition for who can make the most detailed map of the empire. What happens is that some cartographer, some map maker makes a map. And another map maker, in competition to try to make an even better map, makes a much bigger map, which is more detailed. Of course, if you have a bigger map, you can make it much more detailed. This spirals out of control until eventually a map is created, which is the entire size of the kingdom itself. And in fact, the map is so detailed that it is in one-to-one correspondence with the kingdom. Of course, a map the size of the kingdom is completely worthless, so is abandoned and is in ruins. What Borges is trying to tell us is that often we can only make sense of the world by viewing it from a distance, by having some coarse-grained perspective, by zooming out and by understanding it from that point of view. And I think that the promise of mesoscopic quantum gravity is that embedded in the gravitational path integral in semi-classics are statistical signals which allow us to view the microscopic physics of quantum gravity from a distance so that it becomes accessible to us and so that we can unravel some of its mysteries. So thank you so much for your attention.
Thank you, Jordan, for the very nice talk and interesting discussion. We have time for questions.
Hi, Jordan. I have one question.
Yes.
I remember that Witten's paper showed that we cannot find the proper boundary Hamiltonian to describe the black hole state, and it is the in general level and in the context of Einstein gravity theory. But in your talk, you said your approach can describe the black hole state. Do you just mean this for some black hole state, not a general black hole state?
So you see the last part, for some black hole state, not what?
Not a general black hole state. Just say, just for some case you can describe in the larger limit or the weak gravitational constant limit.
Well, the thing, so I assume you're talking about the paper by Witten and Schlenker, right?
Yeah.
So the point of their paper is that you can't actually describe a single eigenstate because semi-classically, because the gravitational path integral has some resolution to it. So you can't, in other words, another way they said this is that there are details of an individual black hole microstate which depend in a complicated way on n, which is not of the form e to the minus n times polynomial and 1 over n. It's more complicated. So therefore, a semi-classical expansion or a large n expansion can't capture that. What I'm saying is that I agree with that, but a corollary of that is that you also can't, relatedly, is that you can't look at a state of fixed energy. What you can do, however, something that does make sense in the large n limit, or the small g Newton limit, is to look at a band of energies, where the band is actually quite large. It's something which is larger than the resolution scale of what the path integral can provide. So in other words, it is not in contradiction. It's very much in line with what he's saying, or with what Witten and Schlenker is saying, because it's saying that you can't access a single eigenstate, but you can access a band of eigenstates. That's the idea. It's a microcanonical band. So that's how you get around it. You just if you have a large enough band, then you can describe that band. But the problem is that if you make the band too small, the semi-classical description fails. There is no semi-classical description of the band small enough. That's also what he was saying. But I just want to observe, just as a comment, that these same things were said, 40 years ago in the context of, billiards and stadiums by Michael Berry in the context of quantum chaos. So it's interesting that we're kind of rediscovering these same ideas in quantum gravity, 40 years later.
Yeah, but I maybe still confused one thing. Usually we expect that the old black holes, classical black hole solution can be described a larger limit. So the you want to say that now it may not be true. It may be it's not the correct idea.
I think what I'm saying is that, well, there's right. Well, in the large unlimit, it becomes imprecise and maybe even really kind of impossible to say what you mean by a particular black hole microstate. I still think that what you can track in the large unlimit is a band of eigenstates. Now, the band of eigenstates, of course, the width depends on n, so it's actually becoming larger. But in some sense, as a fraction of some part of the spectrum, you can still make you can still kind of track what happens to this band. So you can't track what happens to a particular state, but in a certain sense, you can track a band if the size of the band also depends on n. That's the idea here.
Yeah, but in this sense, that some state does not appear in the large unlimit. But if you take the finite n, this state will appear. So this means that it does not have a classical notion, but you can find it from a quantum notion.
Yeah, I'm saying what I'm claiming is you can define a quantum notion of a band of eigenstates in the large unlimit, not a single eigenstate.
Okay. Okay, but I think we don't expect that everything have a classical notion. Okay, but I know what you want to mention. Yeah, thank you. Yeah.
Sure. Yeah, I mean, that's right.
Do we have more questions?
So, so it seems that in your picture, what gravity is in terms of the boundary theory is probably you are connecting two conformal field theory.
Yes.
And then maybe you will have to coarse grain. So these two combination of these two are the I guess the gravity does. Is that what you are suggesting?
What I'm saying is that to get a reliable wormhole in gravity, you have to do something which couples or jointly constrains the CFTs on the boundary side. So let me make a claim, which is a prediction, which is that I told you earlier in the talk that there are other examples of wormholes which don't necessarily have this property that I just said. You know, there's these other kinds of wormholes, although their stability is not known. I predict, or I mean, okay, I'll make a bold claim. I predict that all of the wormholes which don't have this constraint property are going to ultimately be shown to be unstable. And there's actually already evidence that many of them are unstable, so that they don't actually make sense in the semi-classical expansion. My claim is that I've at least shown you an example of something which does make sense in the semi-classical expansion, which is dual to a constrained quantity. But my hope, or my conjecture, I suppose I should say, is that there are no other semi-classical wormhole contributions, or that all semi-classical wormhole contributions correspond to a constrained quantity on the CFT side, and those that don't are not stable and should not be included in the gravitational path of rule.
Okay, and one final question is, so in all your discussion, the presence of the horizon is not really essential?
Well, in a certain sense, I mean, well, let me say it this way. In the Hawking computation, Euclidean gravity, you know, in the cigar geometry, it caps off at the horizon. One way of, so even in the Hawking computation, the one-sided computation, just Euclidean black holes, that, you know, there isn't any, you know, how do I say, you know, the geometry ends sort of at the horizon, if you will. One way of thinking about these wormhole geometries is it's sort of like you take these two geometries, each of which end at the horizon, these Euclidean geometries, and you kind of glue them together and open it up. So there's a sense in which the bottleneck of the wormhole is associated with the horizon.
Right. So, but from the boundary point of view, right? You can just consider zero temperature theory also.
Zero temperature?
yeah, zero temperature conformal field theories are just coupled, and then you can coarse grain it. And there's nothing wrong about it. And why we should consider, I mean,
when you say zero
finite
temperature, you mean the ground state? You mean below the black hole threshold, or you mean the first state?
Yeah,
above?
yeah, right.
Yeah, I mean, I don't think you literally mean zero temperature. Or that would just be the ground state.
Right. Right. So, but still, I guess that we can couple two conformal field theory at zero temperature, right?
Yeah.
And then, yeah, but I guess that what you are saying is that coarse graining doesn't make sense.
Well, also, if, of course, if you have a finite black hole threshold, then zero temperature is below the black hole threshold. There's no black holes. It's just the vacuum. So there's no black hole physics in that state.
Right.
What about then like a supersymmetric black hole, like a PPS black hole, extreme?
Yeah. So I think that you should also see some of the comments by Wood and Schlenker in that case, but I think that some of the BPS black holes are weird in the sense that they contain integrable physics. And I suspect that I'm not exactly sure what the right words are to say about this, but I expect that the very, very special black holes are not actually chaotic in the same way that a generic black hole is.
Or like of course, zero temperature is not clear, but near the PPS, it's you remember recently people talk about that it's not exact PPS, but the slightly excited. That one then.
Yeah.
People
That's
consider super Schwarzschild and so on.
Yeah, that's fine. But I mean literally on the nose, BPS. I mean, yeah, like literally zero. Not near it, but literally on it.
Anyway, I really appreciate the very inspiring talk. Thank you very much.
Thanks.
Are there any more final questions? Sure.
So when you change the coupling between two CFDs, can you see in other measures like entanglement entropy or like these mixed correlation measures that changing one of the coupling in one of the CFD or changing something in one of the CFD regarding to other CFD breaks the correlations? You also...
Yeah, sorry, go ahead. Oh, so yeah, go ahead.
I think you also, that expectation value is kind of a measure of correlation, right? Somehow similar to entanglement entropy or mixed correlation measures. So I expect that we get the same results from those measures too. But do you know anything?
I mean, in Euclidean signature, what it means to compute entanglement entropy is not so clear. I mean, yeah, there's other kinds of things you can compute. I don't know how to compute many other things beyond this. I mean, they're all kind of related to energy correlators, but yeah, so I don't know about entanglement entropy because that's kind of a Lorentzian thing. You really need to kind of have a Hilbert space at fixed time or something like that to talk about a state. So, I mean, one thing you can do, I suppose, is you can imagine kind of deforming. I mean, you can imagine correlators where you perturb the CFTs by other kinds of operators. Like you can look at these kinds of spectral statistics where you perturb by other kinds of operators and get some other information. But I don't immediately know how it relates to entanglement entropy or other things like that. Or sorry, let me say maybe one thing. You could ask what happens if you slice the geometry in half and look at its Lorentzian continuation. Maybe that's one thing you could say. So then it looks like a wormhole, which is supported by some integrated stress tensor. Yeah, anyway, something that might maybe make sense along the lines you're saying is that you can kind of slice the geometry and then evolve it in Lorentzian time, kind of regard it after you slice it in half as preparing some Euclidean state, and then get some Lorentzian type geometry and study that. But I'm not exactly sure what it means.
Let me ask one naive question regarding the wormhole geometries. You mentioned that there are some which are shown to be unstable, so they don't contribute to basically to the computation that you're doing. Are wormhole geometries with higher genus included in this category of geometries that don't contribute?
So the higher genus examples I suspect that you have in mind are like the ones in vacuum ADS3 or something.
Yeah, right.
I mean, the issue basically is that if you actually embed that into, okay, so pure ADS3 gravity is kind of, it's a different animal. But if you want to embed this into something like ADS-CFT, you could look at something like the deformed D1, D5 system. And yeah, there's basically issues when you couple matter and, I mean, there's issues away from the vacuum. That's the problem. It's sort of fine in pure gravity, but not in not in things that are richer than pure gravity. I mean, the pure gravity case is extremely interesting for other reasons, but yeah, I just want to make that distinction. When you have matter fields, in general, you're going to get a problem.
Okay, but do you expect that these? I mean, the picture that I have in mind is somehow that if you're looking at these two-sided wormhole geometries, and you're computing this smeared energy level spacing function. My question was rather, do you expect some contribution to this function from higher genus wormhole topologies or something like that? Like some subleading contributions or something?
I see. I don't. The short answer is I don't know how to compute them.
Right.
And let me maybe mention one other thing, which is related to this, which is why the story is a bit confusing. Well, okay, let me say it like this. You know, in string theory or even in low dimensional gravity, due to the presence of an Euler characteristic term, like a genus counting parameter, that there's suppression of higher genus terms. Yeah. The thing which is confusing in this case is that a priori, there isn't, I don't know what would suppress the higher genus contributions, if there were any. So, I mean, that's also a problem in ADS3 too, by the way. Yeah. Sorry, ADS3, that's also an issue, I should say.
Right.
In pure ADS3, forgetting the matter thing. But I guess that my expectation somehow is that, sorry. So good. So let me make one other comment. Sorry, let me say one other thing. So the thing which is, okay, good. So here's a reason maybe against general higher genus things and higher dimensions, that in general, so it's actually, you have to do quite a bit of work so in these two-side wormholes, the energy constraint stabilizes the modulus that prevents the bottleneck from pinching off. Right. In general, when you have higher genus things floating around, you're going to have more moduli. And it's not a priori obvious that you can stabilize all of them just using, boundary constraints. I think that's the problem.
Yeah, so it boils down maybe to a stability question in some way, or.
Yeah, or I mean, or even not just that, but also whether it's valid in effective field theory. I mean, somehow the point is that like all of the cycles have to kind of be, you know, much larger than the Planck scale.
Right.
And for the gravitational path integral to even make sense. And it just so happens that I think, I mean, of course, in the case of where you have two boundaries, that you can, you know, that you can constrain essentially the size of the bottleneck in that case. But I think when you have more complicated topology, I think that, yeah, I just don't see how it can work. I mean, maybe if you have more boundaries that you can play some game, or if you have more boundaries and more complicated topology, you can play them off of each other in some way. But I think that that's a real serious, you know, I think that that's something that's not in favor of having more complicated internal topologies in effective field theory. Maybe in string theory they're there. I mean, you know, but we can't compute that the gravitational path integral, or, you know, we're not strong enough to do string field theory in the right way, or whatever it is that we have to do.
Right. So I think this would be a good point to stop. So let's thank Jordan again for the very nice talk and inspiring discussion.